I would like to welcome everyone to this informational webinar where we will discuss briefly a IPAM program on mathematical and computational challenges in quantum computing. I will share my slides here with you guys. As I said, this is a program on quantum computing that will be at IPAM in the fall of 2023. And before we talk about the program, I want to say a few things about IPAM. But really before that, I want to introduce some of the organizers of this program who are actually going to, here with us in this webinar. So we have Fang from UC Berkeley. He is there. I think you can see her. Eric Hudson from UCLA, who is not here today. Lin from Berkeley as well. He is here. Hi, Lin. Jerrod McClean from Google, who is also on this call here. Hi, Jerrod. Pranaya Narang from now UCLA. She's not at Harvard anymore. Richard Ross, UCLA. He's also here.
Hello.
And then Dan Stamper from Berkeley and Konstantina Trivisa from the University of Maryland. So we have a great group of organizers for this program. And before I let the organizers talk about the program, I would like to say a few words about IPAM, for those of you who don't know who we are and what we are doing. IPAM is one of several NSF-funded math institutes. We are at UCLA, at the UCLA campus. And it is our mission to bring together mathematicians and domain sciences or different areas within mathematics. And we do this by having activities and we foster the interaction of mathematics with other sciences. Our goal is to build new communities for long programs. When we have different communities, it is also a goal to kind of like bring people together in the sense that everyone speaks the same language, because sometimes you have different domains, people work on similar things, but because they use different words, they don't really understand what they're doing. So we want to break down linguistic barriers. And in general, we just want to highlight, many important mathematical problems. And of course, mathematics and quantum computing is one of them. That's our goal to develop human resources in general, to promote the use of mathematics, promote the use of mathematics in application, and in general, engage and transform the world through mathematics. Our tagline is math changes everything, which we think is a great tagline for all of that. So to just tell you who we are, IPAM has a director, Dima Shlektenko. I am the deputy director at IPAM. Our associate director is Selene Banuelos, and Stan Osher is the director for special projects. And this group of people is responsible for planning and executing all the scientific activities here at IPAM. I described a little bit what our mission is, and then of course the question is, how do you achieve our mission? And here's a very brief summary what we are doing. So the main activity we have, our signature activity, so to say, are long programs. These long programs last for 3 months. And the one we are talking about today is, of course, one of these 3 months programs. I just want to mention that we also have workshops and exploratory workshops that are typically 1 week standalone events. We have summer schools or sometimes even winter schools. We have some other outreach and workforce development programs. We have industrial short courses, and we have undergraduate research programs for graduate students and undergraduate students called RIPS and GRIPS. But as I said, one of the main things we're doing are these so-called long programs. And today we will talk about this long program on mathematical and computational challenges in quantum computing that is scheduled for the fall of 2023. Before I turn it over to Richard, I just want to actually also talk for a second about this pie chart here on the right, just to show you the breakdown of the visitors we typically have of IPAM. And you can basically see that about half of our visitors are from math and statistics, while the other half come from physical sciences, engineering, computer science. This just gives you an idea that participants have a very broad background for IPAM programs, and that's of course exactly what we want to achieve also in this program on quantum computing. So having said all of that, I would like now to turn this over to Richard Ross, who I think will talk a little bit about this upcoming long program and the motivation for this long program before we discuss specifically some of the workshops during this program.
Okay. Thank you, Christian. So good morning, good afternoon. I'm Richard Ross from UCLA, one of the organizers. And so I'll give a brief overview of what the long program is about, and then we'll go into more detail on some of the specific elements of it. So quantum information science is a highly interdisciplinary field that draws from quantum physics, information theory, theoretical computer science, and mathematics. And major progress and milestones in the field have actually long preceded the enormous publicity of late, going back more than 30 years, and some people will say 50 years. So the discovery by Peter Shor of the integer factoring algorithm built on many previous mathematical results, actually, in order finding, quantum Fourier transforms, and the development of quantum adders. The development of many other quantum versions of sort of known algorithms that are quite useful in math and industry include variational eigensolvers, approximation optimization algorithms, linear system solvers, and machine learning. And just as important is the very active foundational work that has gone on over the past number of years in quantum complexity theory. And all of these have relied on a very robust participation of the mathematics community. A notable recent foundational result in the field borrowed from many of the toolkits of mathematical research shown here, these papers by Slofstra and Paulson, showing, basically proofs of the not closure of quantum correlations. And these are these have proved to be very important results in quantum information science. Next slide, Christian. So, and in turn, this abundance of new problems and approaches has inspired a new generation of mathematicians as well as mathematics. So here we list a number of recent case studies where both math has advanced quantum information science and quantum information science has advanced math. We've highlighted in red a number of the participants and organizers in this long program. And, a lot of this various work will sort of has informed the workshops that we've put together and the activities that we hope will sort of take place during this long program. So the purpose of this IPAM long program is to nurture both the existing and to build new relationships, among our various communities, including mathematics, theoretical computer science, theoretical physics, and many others. Okay, so the details. At the very beginning of the long program, we will hold a series of tutorials during the first week. And then there will be four workshops. The first workshop will cover the topic of quantum algorithms for scientific computation. Workshop 2 will be on the mathematical aspects of quantum learning. Workshop 3 will dive into many-body quantum systems via classical and quantum computation. And workshop 4 will go into sort of a variety of topics, including topology, quantum error correction, and relationships to quantum gravity and other topics.
And we will now talk a little bit more in detail about the four workshops. And I think Dee will talk about workshop 1.
Yes, so I am Dee Fang. Our first workshop will be on quantum algorithm for scientific computation. The organizers are Dominic Berry, Dean, who is also here, Konstantina Trivisa together with me. Our main theme is quantum algorithm. As we know that recent development of quantum algorithm has really significantly pushed forward the frontier of using quantum computer to perform a wide class of scientific computation problems. These problems include linear algebra solvers for large scales, such as solve linear systems, eigenvalue, singular value transformations, matrix function evaluation, trace estimation, even topological data analysis, as well as certain high-dimensional differential equations. So this workshop, we aim to bring together leading experts across different disciplines, propose open questions, and pave the path towards identifying and overcoming challenging problems in science and engineering applications. Like illustrated in our logo, these colorful strings indicate potential applications of quantum computers. We really hope to find more interesting applications with promising speed-ups, and we hope you join us on this journey. Thank you.
Thank you, Dee. Jerrod will talk about workshop 2.
Yeah, so workshop 2 talks about basically the mathematical aspects of quantum learning, which I think is a very exciting area that, of course, everyone's seen in the news recently, all the exciting developments about machine learning more generally, and it's always been a question whether quantum computing will be able to play some role there. And so that includes using quantum computers for the processing of classical data, but also in the more recent discoveries, kind of the way in which quantum computers might allow us to learn from data in our natural world to sort of see things that might be invisible otherwise. And I think this brings together a lot of exciting mathematical and learning challenges, and sometimes kind of flips the script where the mathematics of learning teaches us something about our quantum universe. And I think this is going to be a pretty exciting workshop trying to tie all of these different areas together. We have a number of great organizers, and I think it's going to be a wonderful program.
Richard will talk about workshop 3.
Hi, so workshop 3 is on many-body quantum systems via classical and quantum computation. So in some sense, this workshop gets to sort of the original idea of quantum computing, going back to Richard Feynman. The organizers of this workshop are Soonwon Choi, Sophia Economou, Lloyd Hollenberg, Pranay Narang, and myself, Richard Ross. So like the original visions of Feynman and actually Yuri Manin and Paul Benioff, quantum mechanical models of computation and the use of quantum computers to directly simulate physical and inherently quantum systems kind of remains a major goal of this field. So this workshop will focus on a variety of topics wherein quantum and classical computers will be used to attack important problems in many-body quantum mechanics and their technological applications, including things in quantum chemistry, drug discovery, and a variety of other things, material science, and so on. So this will include the mathematics of many-body quantum systems, links to chemistry, condensed matter physics, and atomic physics. And we'll also dive into the study of quantum control theory and the dynamics of current NISQ era and future quantum computing systems to achieve these goals. So this should be a kind of a very sort of broad, wide-ranging workshop that will bring together people from both the classical quantum chemistry and material science communities and the quantum information science communities working on these fields. So we hope you will join us for this workshop.
Thank you, Richard. And Lin will talk about the 4th workshop.
Hi, I'm Lin from the math department at the UC Berkeley. I'm a little bit far away from this area, but I'm very glad to advertise for this workshop. So this workshop is organized by Anurag Antru from Harvard, Colin Delaney from UC Berkeley, Maria Sujan from UIUC, Roman Lachin from Microsoft, Zhenhan Wang from Microsoft, and John Wright from UT Austin. So quantum error correction really is plays a vital importance in quantum computation. All the previous amazing applications, they ultimately hinges on the quantum error correction work. And moreover, in the past few years, there have been very exciting developments in these directions, such as the discovery of optimal quantum LDPC codes that could possibly be used in the future quantum error corrected machines. That there are also very deep theoretical progresses made in this community, such as progress towards the quantum PCP conjecture that sits as the center of a number of important problems in complexity theories. Particularly, there is this proof of the no low energy trivial state conjecture and the invention of the Floquet codes that have been very much being advertised in this community in the past few years. And so this workshop will focus on such new developments with the goal of finding better quantum error correction codes. But quantum error correction really goes beyond quantum computing and plays a vital role in quantum gravity and black hole physics as well. So hope you find this to be interesting and join us with this workshop.
Thank you, Lin. So we've now given you some ideas about the 4 workshops that are a main part of this program. But the program, as I said in the beginning, is really a 3-month program. And very often people ask, well, what happens in the weeks when we don't have a workshop? And is it worth coming? And the short answer is yes. We encourage all of you who are viewing this and others who you talk to really think about coming for the entire program, for the entire 14 weeks. And I just want to talk briefly about what you should expect if you actually come to IPAM for the entire 3 months and not just for 1 or 2 weeks or for 1 or 2 of the workshops. To start with, we have a nice space, and we have space for about 40 to 45 core participants. And that's the number of people we're aiming at to come to IPAM. Everyone who comes to IPAM as a core participant will get an office at IPAM. And, then you can there do some of your own work, but really, I mean, you come to the building every day and you meet with all the other core participants on a regular basis. Typically, the people who come long-term form some working groups, depending on everyone's interest. There will be some seminars that are in particular valuable for the more junior participants, but also, of course, for the more senior people. This way you get a chance to really collaborate and talk to people on a level and in some depth that you can't do in typical workshops or conference you go to that are 1 week, where all you do is you get a chance to talk to someone during a coffee break for 5 minutes. So the idea really is to bring everyone in and have a very relaxed atmosphere such that you can really work together in depth, start new collaborations, write new grants, potentially find your advisor if you're a younger person, and all kinds of things. So in retrospect, most people really say that coming to IPAM to a long program, the weeks between the workshops were really the more valuable experience of the long program compared to just the hopefully exciting talks of the workshops. Just in general, we do want to have people at all seniority levels. Obviously, our organizers who are here with us today are all very senior, but this is open to graduate students, postdocs. So if you're viewing this and you're a student and you're interested in coming, please consider applying to come to this program. The way you come to this program is you can't just register. It's not open for registration in general. You have to fill out an application form, and I will go through this in a second. And then once your application is approved, we will invite you. And once you're invited, we will support all your travel and housing expenses. And if need, we can also discuss about other support that may or may not be needed in your case. So now the question is, how do you apply to come to an IPAM program? And it's actually pretty simple. You just go to our webpage, the webpage of this program, which is listed here at the top, and you go to the application tab, and then you just follow out the application form. It's very straightforward. Things to keep in mind if you apply to an IPAM program, there is a form where you should explain, first of all, of course, you need to put in all your demographics and who you are and so on, and you should explain why you're applying to this program. And I would say there are two things to consider. Some of you might be really experts in this area and you want to apply to come, and of course, everyone would love for you to come because you're clearly going to be a great contributor. But some of you might feel like, well, I'm not really an expert in this field. Is this really for me? And the answer is yes. Even if you're not an expert yet in quantum computing, you should definitely consider applying to this program. And then you should just explain in this application why you want to come to this program, what you think you'll get out of it, what you think you will contribute. And, if, for example, you're not in the field yet, explain that you plan to move into the field or so. When you apply for the program, you also need to submit a CV. And for the more junior people, you also need to submit or arrange for at least one or potentially even 2 letters of recommendation. So that's if you want to apply to come as a core participant to the long program. And as I said in the beginning, we really encourage people who are watching this to come as long-term core participants. And if you have any questions, of course, you can always ask them in a minute or anytime in the next few months when you see this webinar and have some questions. We, of course, also discussed that there are some workshops, and if you can't come or don't want to come to the entire program, you can also come to just one of the focus workshop. For those, it's a little bit easier. There is open registration, so you can just go to the webpage of the workshops and register. Or if you need some funding, you can also fill out an application page, which is very similar to the application I just described for the long program. And you will see it when you get there. And there's also always an opportunity for to give a poster presentation at any of the workshops. And that's, of course, particularly useful for the younger people. So this is really all we wanted to cover today in this webinar, to describe this program, tell you a little bit about what it means to come to IPAM, who IPAM is. And I know there are several people in this webinar who are watching this live. So if there's any questions, we will open this up to questions in a minute. For those of you who are watching the recording over the next few weeks, you can always send an email to me or anybody else among the organizers if you have any questions about the program. So with that, I would like to thank again everyone who participated, and I want to thank the program organizers to join in this webinar. And I hope to see many of you during the program in 6 months. Thank you very much.
Thank you.
Bye.
Thank you.